So we want to calculate the coefficient of static friction that would keep the hoop from sliding ever so slightly right here on the inclined plane, whose angle is theta. So we want to first start with our force diagram. So let's do that. We're going to do a vector that goes from the center of the hoop straight downward. Let me try that again. So it goes from here straight down. It's about right there. And make that an arrow. And then, of course, we have our normal force, which goes from the center up, like so. And make that also an arrow. Like this, we'll label that as our normal force. This will be the weight of the hoop in the direction of the center of the earth. So we'll call that mg. If we draw our components, we'd see that the hoop will want to go this way. So we're going to draw our components this way, like so. And then, of course, in this direction, keeping in mind that our only real force is gravity here acting on the hoop. So the weight of the object is our only force. So then this component here would be our mg times sine of the angle theta, right? Because our angle here is theta, and if because of similar triangles, this angle here is theta, so that's in the y direction on this triangle. And this way, this component here would be mg cosine theta. Okay. Now we know that frictional force F is defined as the coefficient of friction, in this case a static friction, times a normal force. And the normal force, of course, is N. So we're going to say N minus the opposite direction reaction force would be mg cos theta. And because this object is not accelerating up or down in this direction, then this would have to be equal to 0. Okay, so we can solve for n. Here, this would be n equals mg cosine theta. And we can actually substitute that into the frictional force. F equals mu s. And then mg cosine of theta like this. Now, mg sine theta is going in this direction. Something is opposing it. Of course, that would be the frictional force going in this direction. So that friction would be this way. And of course, there's also a tension on this string here, not labeled. We're going to call it T. Now, because this is in static equilibrium, you can see that the force here is like a torque, where the radius of the circle here is our moment arm. So R multiplied by T will be equal to R multiplied by the frictional force. So we can see then that the tension and the frictional force are congruent, or rather equal. So we can say then T is really equal to the frictional force here. So then we can write our components here, mg sine theta minus these two forces, T and frictional force, but those are equal, so that's going to be twice the frictional force. And everything has to be set equal to, I believe, 0. Okay. However, now we have to substitute our frictional force into this equation here. So we're going to have mg sine theta minus twice the frictional force, which is all this over here. Coefficient of friction like this. Multiply that by mg cosine theta equals 0. And as you can see, we can divide everything by mg, so that drops out. Divide everything by mg, and of course if I divide here by mg, it's still 0. So I get sine of theta minus twice the coefficient of static friction times the cosine of theta here, like so. Okay, so if I move this to the other side of the equal sign, I'm going to have sine, one second, the sine of theta equals twice the coefficient of static friction times the cosine of the angle theta. And since we are solving for the coefficient of friction, I can divide both sides by 2 cos theta, because the only thing that was given in our problem was theta. My answer has to be in terms of theta. So that cancels out here, that cancels us there. So then our coefficient of friction is given as 1/2 sine of theta over cosine theta, which can be simplified to 1/2 tangent of theta. And if I simplify it a little bit better, make that mu sub s equals 1/2 tangent theta. This is one of my favorite problems to explain. And I hope that illustrates the use of the coefficient of friction, the vector components, and a little bit of torque involved in there. So all that roll into one problem. Hope it helps.